Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
In this video, we want to talk about strong and weak acids and bases. In the last segment, we learned that there's acids and bases, but there are classifications. You can take an acid and a base and you call them strong, or you call them weak. Now, strong acids, and strong bases, by the way, are like, well, they're like a high school romance. What? What happens to all high school romances? They break up. Now, that may be an oversimplification, but isn't that a lot true? Is that they all break up. So the defining characteristics of a strong acid or a strong base is that they break up completely. What do I mean by they break up completely? So let's say I take a strong acid, HCl, strong acid, and it's a gas. I put it into water, and it breaks up into hydrogen ion, AQ, and chloride ion, AQ. Now, if I were to say that I started with 100 romances, 100 hydrogen chlorides, this is actually hydrogen chloride when it's a gas, all right, what would happen is when they meet the water, how many of them break up? All of them. Zero, or this, you make 100 boys and 100 girls, 100 hydrogen, 100 chlorides, and this number drops to 0. So right, we can draw a graph. Before the experiment, it looks like this. This is the, if you will, this is the HCl, and then here's the H, and then here's the Cl. All right, after the reaction, you have 0 HCl, and then you have 100 H's and 100 chlorides. That's a strong acid. So key thing, strong acids completely dissociate. We've learned about in previous videos about what dissociation is. And this is like a strong electrolyte. Hydrochloric acid is a strong electrolyte because it completely breaks up.
So I have a molecular model that represents hydrochloric acid, HCl. And HCl is a strong acid, one of the 6 strong acids that exist, or well, there's more than that, but for our purposes. So what that means is that it completely dissociates. So if I take this HCl, which typically is found as a gas, as I've symbolized here in the chemical equation, if I drop it into water, it will dissociate completely into hydrogens and chlorides. That means it's going to break apart into hydrogens and chlorides. Now, if you notice over here, I've got a whole bunch of HCl's. When I say completely dissociate, that means all of them will dissociate. So I would break apart this one. So what they look like is, well, all the yellows, all the hydrogens, are broken apart from the chlorides, and they're completely dissociated. Now, this is actually not the way they look, because they would all be mixed together. They'd all be mixed together and be randomly placed in the compound.
But what's a weak acid? An example of a weak acid is hydrofluoric acid. And if we take this as a gas and we add it to water, we now draw a double arrow and it breaks into H's and F's. We do AQ here. And it only partially dissociates. So if I start with 100 of these, usually I think HF is about a 5% breakup rate. Okay, and so you start with 100, let's say 0 of this, and what happens is only 5 of them break up, and you end up with 95 HFs, couples if you will, to use an example, and then you add 5, we get 5 of each. So if we were to draw a graph like we did before we added it, we have 100 HFs, 0 H's and 0 F's after the reaction, and then you'd have 5 H's and 5 F's. It partially dissociates. So it doesn't completely dissociate, it partially dissociates. It's a weak electrolyte, so if you were like to put the light bulb test in there, it would light up the light bulb just a little bit, where the strong electrolyte, if it was a strong acid, would completely dissociate.
So here I have an example of a weak acid from a molecular model. It's acetic acid, HC2H3O2, and so the yellow here represents the hydrogen, and the red is the acetate. It'd actually be more complex than this, but that's close enough. And so what it's going to do is it's going to partially dissociate. That means that only some of them, when added to water, will break apart into hydrogens and acetates. So I'm going to break apart one, And frankly, that's probably about right. What's going to happen, most of them stay together as HC2H3O2, acetic acid, and a very few break apart. Usually it's 1 in 100, maybe 1 in 5 out of 100, so it's like 1% or 5%, sometimes less than even 1%. So this is an illustration of a weak acid that partially dissociates.
So how do you know if you have a strong acid or a weak acid? Good question. Turns out almost every acid in the world, universe, is weak. So if you know the list of strong acids, then you're gold. So let's list the strong acids. Strong acids, there's just a short list here. And this might be not complete, but I'll give you the most common ones we'd see in a chemistry class. HCl, hydrochloric acid, strong acid. HNO3, nitric acid, strong acid. That's it there, guys. There's 5. Hydrochloric acid, nitric acid, sulfuric acid, perchloric acid, hydrobromic acid. These are the strong acids that you need to know. There's a couple others, not that important. But if you think about this, if you see that's your strong acid, if you see any other acid, let's not talk about strong and weak bases. Strong and weak bases. Similar deal. Guess what? A strong base breaks up completely. A weak base doesn't break up completely. Same idea. So strong and weak. So let's do like a strong base. The classic strong base is sodium hydroxide. We talked about that earlier. It's a solid. You drop it into water, it makes Na positive and OH negative. Note again, hydroxide is what makes a base. It completely breaks up. A classic example of a weak base, and this is a weird one, is ammonia. Now, if it's supposed to make hydroxide, there's no O's. That seems odd. But this is really one of the most common bases. I'm going to react that with water. In this case, I'm going to write water, but I'm writing it as HOH. Draw the double arrow. The double arrow is also a way to tell if it's a weak or a strong acid or base, in this case a base. And what's going to happen is the H is going to move from here to here, and it's going to make NH4 positive. I don't know if you see that, but then it kicks out a hydroxide. In fact, most of the common bases have like a nitrogen in them. They're called amines. Amines. I think that's Greek for nitrogen. Anyways, this is a common strong base. Now, similar to strong acids, there's a list of strong bases. There's not very many of them. Ultimately, they're the alkali metal hydroxide. So lithium hydroxide, right? Our first column on the periodic table, sodium hydroxide, potassium hydroxide, and sort of kind of in between, between strong and weak, you can find the lower parts of the periodic table. You could have calcium hydroxide, CaOH2, and this is kind of a debatable one, whether it's kind of not quite strong, not quite weak, magnesium hydroxide, etc. All the rest of them are weak.